Hello everyone, and thank you for attending this section. I'm the Chen Lai Harry. I'm from the Chongyuan Christian University in Taiwan. It's my pleasure to present our work on the enhancing students' understanding in computer programming by using a visual programming system, specifically designed to address abstract and difficult topics in the C programming. This presentation is based on the classroom-based study we conducted with the undergraduate students, and the system we developed aimed to fill the gap between traditional textual programming and the students' cognitive understanding, especially for a topic like arrays, structs, and linked lists. Our goal is to provide a learning environment where students are not only writing the code but are truly seeing and understanding what happens when the coding executes. We believe this visual approach can significantly strengthen students' programming literacy, especially for beginners. This is the background of programming educational challenge. For this challenge in the programming education, as many of you know from experience, learning to program is not just about syntax. It involves learning how to think computationally, how to debug, and how to mentally module the way the computer processes code. Students often struggle with the syntax memorization, with the created unnecessary mental load. For the local flow, especially with the conditional and the loops, abstract concepts like the memory allocation, reference, and the point. In Taiwan's education context, most high-school students learn only very basic ICT or block-based logic. When they enter the university and face C programming with the pointer and the struts, the jump is the step. This mismatch between the prior exposure and the university level complexity creates frustration. While many platforms exist, such as the LibCourse for the practice, Berkeley or Scratch for the visual logical, they either oversimplify or don't offer the detailed execution. For this detailed execution for the level understanding, that's where our visual programming system comes in. So for our system, we are designed with a specific goal to bridge the gap between the code and the mental model. It's not just another bracket coding environment. It simulates how a program actually runs step by step with the visual representation of the memory change. Here are the three core features. First is the visualized execution. Students can create code via drag and drop the components like if, while, function, memory allocation, return, etc. And then watch the program animate during execution. And the second feature is the memory visualization. The system shows a clear separation of the global and the local scope, displays the variable types, addresses, and even point links in real time. And the three feature is the playback controls. For this feature, it's like a debugger. Students can run forward or backward to better understanding runtime behavior. The system doesn't require the prior coding knowledge. it lowers the entry barrier and emphasizes conceptual correctness over syntactic precision. So everyone can see this picture is the system user interface. You can see the on is the switch and the n the function. And this is the code block. You can, in this code block, write your code, and when you enter this play button, it will display the runtime for this program, the procedure in the workspace block. And this is operation block. You can enter some variable or reference for the number or the variable. And this is the other variable block like the if, the for, and the function and the while memory allocation written like this. And this is the visualizing arrays, try, and the linked list for the operation. Here's what the visualization look like in the practice for arrays. Students can specify the size, assign value to the to point, and observe how arrays behave in memory. The system shows both array declaration and the actual memory layout. For structs, we color code different fields by type, integers, characters, and pointer, so students can visualize separate components. The layout minimizes how structs and the star are stored in the memory. And this is for the linked list. This is the while the students choose creating node with the memory allocation, connecting points, and the traversing through while loops. All these are animated. Students can see the creation of the list, node linking, and the traversal step play out visualized. By watching how a list nodes move, point to the next, becomes a node, etc., students develop spatial intuition for how points work, which is often missing in text-only code editor. For this is experimental design and the student participation. So we want to evaluate the system's effectiveness. We conducted a classroom study involving 88 freshmen enrolled in the Introduction C programming course. Here's what we did. First, students attended a 30 minutes demo of the visual programming system. Then they download the tool and use it independently over 2 weeks, while learning arrays, structs, and linked lists in class. After this period, we gave them a 15-item questionnaire. The assess the perceived understanding and usability. The questionnaire was statistically reliable with the Cronbach alpha is 0.846, which indicates the high internal consistency. We intentionally allow open-end usage, so students could apply the system to homework or deploy it freely, reflecting a realistic integration into a learning rather than a control lab test. Now this is the key finding the student feedback. So let's look at what students say. The feedback was largely positive. For the 78.8%, say the system helped them understand how program executes, and the 77.5% feel is classifying the basic C programming concepts, and the 70% reported the better understanding of advanced topics such as array and functions. And the 66 say it helps reinforce the classroom interaction. We also found the students who were weaker in the math or the logical skill particularly benefited from the visual breakdown. And one student even commented, "I finally understand what memory allocation does. I used to just copy and paste and without knowing what it meant." This results reinforcing the idea that visual learning can complement the traditional coding environment. So we trust our research can help the students to improve their programming concept and enhance their learning motivation. But for our research, there are some limitations and the student preference. Of course, the system is not perfect. Only the 25% of the students feel it improves their actual programming skill, meaning that while it helps with understanding, but it might not prepare them directly for coding interviews or time contests. So we will say this visual system can improve their coding or we say programming concept, but for their implementation, it is not truly to help them. And also, only the 24 preference is over leaf code, and the 37.5% say that link is more than the diversity judge. And some notes the most basic control will like weekly, and the span control or animation were too fast. We also noticed the system with a strong prior experience found the system too slow. So the takeaway is that the tool is best suited for a beginner or conceptual learner, and might not appeal to advanced students as thinking, coding, visual, or syntax validation. So in our conclusion and the future direction, our visual programming system is effective learning compassion that enhance the conceptual understanding, especially in areas like the memory management and the point logical. It supports the learning by turning invisible execution into the visible feedback. It empowers the students who would otherwise be lost when reading pure code. However, it should be seen as the complement, not a replacement to text-based coding platform. It lacks the features for syntax training, comparative feedback, and the performance text. So for future work, we plan to run control A or B the experiments, the comparison visual versus traditional learning on the assessment outcomes. And the second is add features like auto-generated memory diagram or flowchart builders. And the third is explore the integration with the code added like the VS Code, and to allow the dual model. Like for their dual model is the text and the plus the visual learning. I think to make this improvement or change will make the student in their performance will to be enhancement. And before closing, I'd like to take the moment to acknowledge to the incredible effort to our research team. The the success of this educational tool and study was not an accomplishment by one person alone. It was a result of the close collaboration between the faculty members, the graduate students, and the undergraduate research assistants in our lab. So, from system design, user interface testing, animation, logical to data collection, and analyze every stage of the development, rely on the dedication and the creativity of the team. This project reflects what possible when the educator, students, and the researcher will work together to improve the computer science learning. I'm truly grateful to be part of such a committed and the passionate team. Thank you again for your attention, and I welcome any question. Thank you, everyone.